Welcome to the video about finding real zeros of a polynomial function. In this video, we'll be looking at using the rational root test and Descartes' rule of signs to find the real zeros of two different polynomial functions. First, let's just review the rational root test. So if we have a polynomial function p of x with integer coefficients in this form, where the coefficients are real numbers, in this case integers, the degree is greater than or equal to 1, the constant term is not 0, and the leading coefficient is not 0. If p over q is a rational zero of p of x, then that means that p is a factor of the constant term a naught, and q is a factor of the leading coefficient a sub n. It's also important to note that p over q will be a fraction in lowest terms. The next thing we'll be using is Descartes' rule of signs. This tells us the number of possible positive and negative real zeros. The number of positive real zeros of p of x is equal to the number of sign changes of p of x, or it's less than that by a multiple of 2. So we're going to count how the signs change positive to negative from term to term, and we're going to either have that number of positive real zeros, or we can reduce that by a multiple of 2. So we'll keep subtracting 2 until we get down to 1 or 0. The number of negative real zeros of p of x is equal to the number of sign changes of p of negative x, or it's less than that by a multiple of 2. So here we have to first plug in negative x for x, then count the sign changes, then subtract 2 until we get down to 1 or 0 to give us a possible number of negative real zeros. Now this tells us about the number of real zeros. These zeros can be rational or they can be irrational. So we're going to use both the rational root test and Descartes' rule of signs to help us find the real zeros of two polynomials. Here's our first example. P of x is equal to x to the third plus 4x squared plus 3x minus 2. First, we'll look at the rational root test. To find the p's, we look at factors of the constant term, which in this case is negative 2, and the factors of negative 2 are plus or minus 1 and plus or minus 2. Then we'll look at the factors of the leading coefficient, which is positive 1, so the factors are only plus or minus 1. Then we form the rational roots p over q, or the possible rational roots. We take all of the p's and divide them by all of the q's. In this case, we only have plus or minus 1. So our p over q's are plus or minus 1 and plus or minus 2. These are the possible rational roots. So that means if we have any rational roots, it will be one of these 4. It does not mean that all 4 of these are rational roots. Remember, this is a degree 3 equation, so we can only have at most 3 real zeros. Alright, now to use Descartes' rule of signs. In p of x, we count the sign changes from term to term. So I have no sign change, no sign change, here's one sign change. So I have one sign change, which means that p of x has one positive real zero. I do not have to reduce that by a multiple of 2, because if I subtract 2 from 1, I get a negative, and I can't have a negative number of zeros. Next, to find the number of possible negative real zeros, I am going to first find p of negative x, and to find that, all I need to do as a shortcut is to change the signs of all the terms that have an odd degree. So p of negative x is negative x to the third plus 4x squared minus 3x minus 2. Counting the sign changes, I have one sign change, 2 sign changes, and a total of 2 sign changes. So that means that we have 2 or 0 negative real zeros. So this is where reducing by a multiple of 2 comes in. I counted 2 sign changes, but then I subtracted 2, so I have 2 possibilities for the number of real zeros. And the reason why we subtract 2, by the way, is because we could potentially have some complex zeros, and they always come in pairs or in twos. So if we're going to reduce the number of real zeros, we will always reduce it by an even number. Alright, so the next thing for us to do is to test a possible rational root. So you're going to go to your list of p's over q's, think about what Descartes' rule of signs tells you, and pick one of these roots and test it. Now you can test it using synthetic division, as I did here, or you can of course test it by just plugging it into the function and seeing if you get 0. I like to use synthetic division because I think it's a little faster. I don't have to worry about exponents, and if I do get a root, then my next step is already done for me. So here you get to pick what you want to start with. Now if you know you have one positive real zero, you may want to start with positive numbers. However, remember that that means that we have a positive real zero. That real zero does not need to be rational. So if you test positive 1 and positive 2, you will not get a remainder of 0 when you divide synthetically. And if you plug in positive 1 or positive 2 into your function, you will not get a 0. Now, I also know that I have either 2 or 0 negative real zeros. So if I have, or if I want to think of this as taking a gamble, I have to kind of decide, well, what do I want to test first? And I have the potential for more negative zeros, so maybe I would have decided to pick a negative value first and then test that. No matter what you test first, the only one that will work in this case is negative 2. And again, sometimes there are more than one rational root that works, but in this case we only get one that works, and that's a negative 2. I know that it works because when I divide synthetically, I get a remainder of 0. Now, if negative 2 is a root or 0, that means x plus 2 is a factor of p of x. And I can now factor p of x, or begin to factor p of x, by x plus 2, and then I use the coefficients that I get from dividing synthetically to get my quotient polynomial here, x squared plus 2x minus 1. Now, if that trinomial that I obtained was factorable, I would go ahead and factor it further. However, it's not factorable, so if I want to find the remaining zeros, I'm going to set this polynomial equal to 0 and solve it using the quadratic formula. So that means that my zeros are the following. Negative 2, that's my rational 0 that I first tested. And then I have negative 1 plus square root of 2 and negative 1 minus square root of 2. Those are two real zeros. Notice the sign of each of them. One of them is negative and one of them is positive. And if I count up the number of zeros I have 3, and that's equal to the degree of this polynomial. So I know that I actually have found all of the zeros of this polynomial. Alright, let's take a look at our next example. Another third degree polynomial, p of x is equal to 3x to the third minus 5x squared minus 8x minus 2. So we're getting our p's and q's. Our p's are the factors of negative 2. Our q's are the factors of positive 3. When we put p over q and simplify, we have plus or minus 1, plus or minus 2, plus or minus 1/3, and plus or minus 2/3. These are the possible rational roots. Counting sign changes in p of x, we again have one sign change, which means we have one positive real 0. P of negative x has two sign changes, which means that p of x has 2 or 0 negative real zeros. So again, I have to use that information to decide what do I want to try first. And again, maybe you want to try integers first. And I definitely understand why you'd want to try plus or minus 1 or plus or minus 2. And I did try those, but neither of those roots were zeros. Or excuse me, I shouldn't call them roots then. Neither of those rational numbers were zeros. They did not give me a remainder of 0 when I divided synthetically. The first one that I got that gave me as a remainder of 0 was negative 1/3. So since negative 1/3 is a root, that means x plus 1/3 is a factor of p of x. So I'm rewriting p of x in factored form, x plus 1/3, and then the quotient that I get from dividing, 3x squared minus 6x minus 6. Now, if this polynomial were factorable, aside from just taking out the GCF of 3, then I would go ahead and factor it completely. But the only thing I could do was take out that GCF of 3. And you could certainly do that and then go ahead and use the quadratic formula, or just use the quadratic formula from this stage as I did. And when you solve, you'll get 1 plus or minus square root of 3. So that means the zeros are negative 1/3, that's our rational root, and 1 plus square root of 3, and 1 minus square root of 3. Those are also real zeros, but they are irrational numbers. Okay, so I hope you enjoyed this short video about how to find real zeros of polynomial functions. Again, we're using everything that we've seen so far, rational root test, Descartes' rule of signs, synthetic division, to find the real zeros of a polynomial function.